This is Cycle 2, Lesson 10. It is the last of our combining functions lessons. It's also the last lesson of Cycle 2. So let's jump in, and we've already looked at adding, subtracting, multiplying, and dividing functions. All that's left is something called composite functions. A composite function is a function that depends on another function. It's formed when one function is substituted into another function. So now we're placing functions into functions. Remember, using function notation, if I have something like f at x, it means that I'm going to substitute something into x everywhere in the function. And it doesn't have to just be a number. I could substitute a variable in for x in f at x, or I could substitute a whole other function in for x. So let's just talk about, well, the notation a bit first. This is how you're often going to see it written, and it's read as f of g of x. So we can read it from left to right, f of g of x. You know, that makes sense. If we just look at this part, we know that's g of x, and then it's inside f of x, so it's f of g of x. Sometimes you might also hear me call it f at g at x. Just another way of saying it. And again, it gives you the order really to think about how you're going to approach things. You're going to work from the inside out. You're going to find out what g of x is first, and then you're going to find out what f of that answer is to get your final answer. Note that the order of functions is important. As read from left to right, the second function is substituted into the first function. Here's a different way of writing it. This still means f of g of x. Just alternative notation means the exact same thing. That little circle is going to mean f of g of x. So let's do some examples, as always, to help us understand it. So if we got two functions, and f at x is just a simple one, x squared, and g at x is also a simple one, it's just x plus 3. Let's see how we can combine these two functions together. So, and we're going to give the domain and range, and we're going to sketch it. Pardon me. So we want f of g of x. So that means we're going to stick g of x into f of x, as you know, this really indicates. You can see that g of x is in f of x. So we're going to just replace g of x with x plus 3. So really we want f of x plus 3, but f of x is x squared, so really it's just going to become then x plus 3 squared. So normally I might leave out this middle step here because we don't need to show that, but that's what it's coming down to. And so we've combined this, and it's still a quadratic. F of x is still a quadratic, but it's a bit different now, right? We know from grade 10 that x plus 3 with the 3 in the brackets moves the vertex over to negative 3, and it hasn't been moved up or down. It's still following the same step pattern, so it would look like this. And as far as domain and range goes, we can see, being a parabola, that the domain's all real numbers, the range is all real numbers that are greater than or equal to 0. Oops, 0. And we're done with that one. Let's see what happens. How is it different if I put f of x into g of x? So now we've changed the order around, right? Here's f. In the first one we had g of x in f of x. In the second one, we've got f of x in g of x. So that means that we're going to have g of x squared. And when I put that into g of x, I get x squared plus 3, or just x squared plus 3 without the brackets. I'm just using the brackets to show the substitution in this case. When we graph this one, it's no longer shifted to the left, it's a parabola that's been shifted upwards. so we have a different outcome. The domain is still all real numbers, but the range, of course, is different because the vertex has been shifted upwards. Now we have all real numbers that are greater than or equal to 3, because that's where the lowest point, the vertex of this parabola is. So, different order gives different outcome. Here's some more using the same functions. Just a reminder, maybe I'll write them up here at the top. Remember, f of x was x squared, and g of x was x plus 3. And I highlighted them just because that might be helpful. Now we want to do f of x. We're sticking something into itself. And that may seem weird, but we can do it. So if f of x is x squared, I want to find f of x squared. So I'm sticking x squared into x squared. And if you remember, when you multiply powers, not multiply powers, raise a power to another power, you multiply the exponents. And now we've got x to the 4. And remember what the graph of that looks like, sort of like a parabola. It's still going to have its vertex at 0, 0, but it's going to be a bit boxier. It's going to have the point 1, 1, and it's going to have the point 2, 8. So it's going to go up more quickly. No, actually 2, 16, my mistake. Because if I stick 2 into that, 2 to the exponent 4 is 16. So it's going up very quickly. I can really only show these points here, and then it shoots up off the graph. Like that. Domain, all real numbers, though. Range, all real numbers greater than or equal to 0. If we do g of x, what happens now? That's the same as g of x plus 3, which means that we're going to put x plus 3 in for x, and we still have the plus 3 from the outside function. When I take the brackets off and simplify it, that becomes x plus 6. So now, this one combines to give us a linear graph. It's going to have a y-intercept of 6, a slope of 1, so it'll look like that. Domain, all real numbers. Range, also all real numbers. Now we want g inverse of g of x. So we have to remind ourselves how inverses work. When we're dealing with an equation, we want to switch x and y and then solve it again for y. So I need to know what the equation of the function of g inverse is. So I'll do this maybe over here on the side a bit. Yeah, let's do it over on the side. So inverse of g of x so if I start by swapping out g with a y, so I just got x and y, so it becomes y equals x plus 3. Now remember, when you're doing the inverse, you switch x and y. So I'm going to put x over here, and I'm going to put y over here. That's how we calculate our inverses. Now I resolve for y. This is a simple rearrangement. I'll just subtract 3 from each side. I only colored them in red so you can see where I was swapping them out. There's no deeper significance to that. So y equals x minus 3. So it turns out that the inverse of g of x is x minus 3. I can go back to function notation. So there's my inverse. It's not my answer overall, but it is my answer for, or it's what I need to help me get there. So I'm putting g of x into g inverse of x. So my first step then is I'm going to take g of x, which was x plus 3, and then I'm going to stick it into x for in the equation x minus 3. And when I take off the brackets and simplify it, I just end up with x. And that's just my starting value. You know, whatever number, if you want to think of x as a number, if say x was 5, if I put 5 into this equation, I'm going to get 5 back out. In other words, my x and my y, if I think of it as ordered pairs, are always going to be equal. It's going to give me a function that looks like, when I graph it, it's going to look like that. Not quite like that. I think I missed something here. Let me make it line up better. Okay, it's going to look like this. That's better. I did a better job of making it go where it should go. It's the line y equals x, isn't it? Because that's literally what it says here. Y equals x. So it brings up an interesting thing about inverses. Inverse functions, as you know, or you should remember, always undo their original functions. They're always the opposite operations in the opposite order. So since inverse functions undo functions, when I put a function in its inverse, they're just going to undo each other, and I'm just going to be left with what I started with, my starting value. And so I'll always get just this line y equals x. And the domain and range of y equals x are both just all real numbers. Okay, last example. Evaluate a composite function like this. So here's a function u at x equals x squared plus 3x plus 2. Here's another function w at x equals 1 over x minus 1. I want to find u at w at a particular number. I would say the easiest way to do this, it'll make it a lot easier, well, much simpler on you, so you don't have to worry about complicated looking formulas, is do it in steps when you get something like this. So I would find out what w at 2 is first, because that'll just be at some number. W at 2 is going to end up being 1 over 2 minus 1, which equals 1 over 1, or just 1. And now that I know that w at 2 equals 1, I can then substitute that in for w at 2. In other words, I can go back and go u at w at 2 is equal to u at 1, right? W at 2 equals 1. And u was x squared, so it becomes 1 squared plus 3 times 1 plus 2. So 1 plus 3 plus 2 equals 6. Like I said, I could do it where I ignore the 2 to start with and put 1 over x minus 1 into x squared plus 3x plus 2, simplify that down as much as I can, and then stick the 2 in there, which I might do if I had to evaluate a whole bunch of numbers. But if I just have this one number, it's certainly easier to do it this way. Likewise, for this one, I would find out what u at negative 3 is. And that's going to become negative 3 squared plus 3 times negative 3 plus 2. So 9 minus 9 plus 2 gives me 2. Then I would substitute that into w at u at negative 3. And I just have to do w at 2. And w at 2, we happen to have already seen, that's just 1 over 2 minus 1. So that becomes 1 over 1, or 1 as my answer. So that's how I would recommend doing it if you got a specific number as opposed to just an x to fill in.